Assalamu alaikum everyone, Afzal Badsha is here, and today in this video I'm going to discuss the trees in data structure. When we discuss trees, it means that it is a hierarchical data structure. In trees, data are stored in hierarchical data structure just like a tree. Okay, my drawing is very bad. This is the root node, and these are the children of the root node. Okay, the related terms with trees are the path, root, parent, children, sibling, etc. I'm showing you the tree here. You can see that this is the root node. A is the root node, and the root node has two children, B and C. Okay, so B and C are sibling, and their parent is A. Okay, and further the B has other two children, and also the C has two children, F and G, which are sibling, and the nodes which have no children are called the leaf node. Okay, the children which have no children are called the leaf node. When we discuss the level, then the root is always on level 0. The children of the roots are on level 1. For example, the B and C are on level 1, and here the D, E, F and G are on level 2, and the H, I, J are on the level 3. Okay, this tree consists of 3 levels: level 0, level 1, level 2 and level 3. When we discuss the height of the tree, that it starts from the leaf node. For example, the height of this is 0. Okay, this is height 0, h0. This will be h1, this will be h2, and this will be h3. This means that the root of this tree is on height 3. Okay, now here the leaf nodes are the nodes which have no children. Leaf nodes are those nodes which have no children. Here you can see that H, Hij and Fg are the leaf children because they don't have further childs. The subtree. Okay, what is the subtree? Here you can see that A further has one subtree, which root is B, and here this is the right subtree. Okay, and we can see that here is another subtree. Visiting any one node and checking its data, populating its data is called visiting. And traversing means visiting the nodes, passing through from the nodes. And level, as I discussed, that the level start from 0, from the root, then 1, then 2, and then 3. Okay, and the height is inverse of the levels. For example, it starts from 0, but from the lower point 1, 2 and 3. Okay, and key discusses the data which is stored in the nodes. Okay, so the type of trees are the boundary tree, avial trees, spanning trees and heap trees. And in this video we will discuss everyone here. Binary search tree. When we discuss the binary search tree, it means that every node have two children, and the condition on the binary node that the left child must have a value less than its parent. For example, here the value of parent is 27, then all the values which are left hand will be lower from 27, and all the value which are on the right side will be greater than 27. So we can see that 14 is lower than 27, and in this subtree we can check that 10 is lower than 14 while 90 is greater than 14. And on this right side subtree we can see that 31 is lower than 35 while 42 is greater than 35. These are the basic rules which are applied on the binary search tree. Operations on the binary search tree are the insert operation to insert any atom, to search any particular atom, and pre-order traversal, in-order traversal, and post-order traversal. These are very important. We will further discuss it. For example, we have one tree. This is A, and this is node B, and this is node C. Okay. Now the pre means that the root node will be, the parent node will be visit first. For example, here we will visit first A, then we will visit left, then we will visit right node. Okay, and the in order means that the head node, the parent node, will be visited in the center. For example, first we will visit B, then we will visit the root node, the parent node, which will be in the center now, because we are discussing the in order, and at the end right will be visited. And in the post order visited, first the left will be visited, then the right node will be visited. Actually this is a C. Okay, this is a C, and after that A will be visited, and we will discuss it in detail. This is a binary search tree. This is a binary search tree, and if we are going to insert 20, then how we will insert? We are going to insert 20. So first we will compare this 20 with 27. Is it greater than from 27? No, it is not greater. So we are not going to the right side. Is 20 is less than 27? Yes, it is less. So we will come on the 14. Now we will compare the 20 with 14, and we can see that is 20 less than 14? No. So we are not going to the left side. Is 20 greater than 14? Yes. So we are going toward the 19. On the left side, is 20 less than 19? No. So no, we are not going to the left. 20 is greater than 19, and 19 is the leaf node. So we are going to add it here. Okay. With this way, we can insert the node, and the same method will be used to search a node in the binary search tree. This shows the full binary tree. Full binary tree, you can see that every node have two children. Every node have two children, and the most important is that all the leaves are full. All the leaves are full. And here in the complete binary tree, we can see that every node have two children, but the leaf level is not full. Okay, so this is a complete binary tree, and this is a full binary tree. Here we are going to discuss the spanning trees. The spanning tree is the subset of graph which has all the vertex covered with minimum possible number of edges. Hence, a spanning tree doesn't have cyclic and it cannot be disconnected. So spanning tree, main thing with the spanning tree is that the we should have minimum possible number of edges. For example, if we are going to have 3 nodes, then the minimum possible edges which are required to connect these nodes are the 2 edges, because adding 2 edges will connect with each other. Cycle, and it cannot be disconnected. It doesn't have cycle, because we are going to connect these nodes with the minimum number of edges, so there will be no cycle. For example, the minimum no edges required are 1 and 2, but if we are going to add the third one, then the cycle will be created. Okay, for example, here we have A, B and C. We have 3 nodes, so the minimum edges required are 2, so we connected it with 2. So if we are having 3 vertices, if we are having 3 objects, then how many spanning trees we can create? So we can create 3 different type of trees by using this formula. Okay, so the important with the spanning tree is this one, minimum possible number of edges are required. For example, we are having 3 nodes, then we are using only 2 edges, and the second thing is there will be no cycle in the spanning trees. So the important properties of the spanning trees are that a connected graph G can have more than one spanning tree. If there is a graph and this is a connected, then there may be possibility of more than one spanning trees. All possible spanning tree of graph G have the same number of edges and vertices. Okay, and a spanning tree doesn't have any cycle, which is actually this is very important, that the spanning tree doesn't have the cycle as I draw in the previous one. For example, I'm going to connect these nodes, then the minimum nodes are required, the minimum edges are required to connect them, and there is no circle in them. Removing one edge from the spanning tree will make the graph disconnected. As you can see that this is connected now, but if you remove the one edge, because we are going to use minimum edges, then this will be disconnected. For example, I remove this one, then you can see that this node disconnect from the previous nodes. And the further is adding one edge will create cycle. For example, I'm going to add this and this will create cycle, okay, which is not required in the spanning trees. Spanning trees required n-1 edges. For example, 1, 2, 3, where n is the vertices. Okay, n is the vertices, and n-1 edges are required. For example, there are 3n, then we will require 2 edges. Okay, we will require 2 edges. And if we are going to 5 nodes, then we will require 4 edges to connect them with each other. And a complete graph can have maximum n-2 number of spanning trees. So how many number of trees can we create? For example, these are 3 nodes, then 3 power 3 minus 2, which is equal to 3. It means that from 3 nodes we can create 3 spanning trees. When we discuss the boundary heap, and in the boundary heap we take the balanced boundary tree, and the other important thing is that the root node is compared with the children, and according to the compare, the node will be set accordingly in the form of minimum heap and the maximum heap. If the root node is minimum, then the heap will be called minimum, and if the root node is maximum, then the heap will be called a maximum binary heap. As you can see here that the root node is 10, left one is 14, this is 19. As you can see that it is in a series, but the root node is minimum, because the root node is minimum 10, 14, 19, 26. It is just like accordingly as the array. If you want to write it in the array, then we will write as a 10, 14, 19 and 26, 31. Okay, but the main point is that its roots have minimum value. Because its root has minimum value, so it will be called a minimum heap. In the next slide you can see that the root node have maximum value and all the other values are less than the root node, so this will be called a maximum heap. So we can define that binary heap will be two types: minimum heap or maximum heap. Okay, this is the binary heap. As you can see, 0 1 2 3 4 5, and you can see that this is a minimum heap. And if you want to return the parent node, then the formula is I minus 1 divided by 2, and this will be the floor function. For example, here I am working under 3, then I minus 1 means 1 minus 1 divided by 2, and its ceiling function, it will be equal to 0, which clearly shows that its parent is 1. Okay, and here return the left child. To return the left child, the formula is 2 multiply by I plus 1. For example, I am discussing 3, then here 2 multiply by 1 plus 1. So 2 equals 2 plus 1 is 3, so this is the left child. And if we are going to discuss the right child, then the formula is 2 multiply by I plus 2, 2 multiply by, for example, 1 plus 2, then 2 and 1, 2 plus 2, 4, which is the right child. And we can directly write this into the array. For example, 1 2 1 3 6 5 9 8. So minimum heap can directly be written into the array. Okay, thank you so much for watching. This was all about the trees and data structures.